Welcome to another deep dive. We're tackling some pretty big questions today. We're diving into climate science, and it really gets at understanding our planet in a fundamental way. And that ties in perfectly with what you've been thinking about lately, acting as philosophers.
That's a great way to put it. You've sent over a ton of material on climate science. It's a lot to unpack. But at its core, it's about how Earth's climate system actually works. Why we have deserts in some places, rainforests in others.
Exactly, and why those patterns change over time. It's mind-boggling how many scientific disciplines come together in this field. It's not just meteorology, right? It's oceanography, physics, chemistry. It's like a giant puzzle,
Yeah.
and everyone's bringing a different piece to the table.
Yeah, it really is a team effort to figure out this incredible complex system.
Our goal today is to dig into all those sources you shared and try to pull out the most important insights. It's like we're giving you a crash course in understanding climate science, but with a focus on those deeper, more philosophical questions that underlie the whole endeavor.
Right. And those philosophical questions are what make it so interesting, right? How do we even know what we know about something as vast and complex as climate?
Exactly. So let's start with the very nature of climate science itself. Your sources point out a real evolution from what they used to call climatology to what we now call climate
And
science.
it's not just a name change, right?
No, it's much more than that. I mean, think about it. The old climatology was kind of like a descriptive science, sort of like geography, focused on classifying different climate zones and crunching a lot of weather statistics.
So it was really about describing what was there, kind of like creating a map of Earth's climates. It was what they call it an inductive approach, right? Just observing and recording.
Exactly. But the key insight here is that modern climate science goes way beyond just describing. It seeks to actually explain why climates are the way they are and how they change. It's about uncovering those underlying mechanisms and processes.
And to do that, it relies heavily on what? Theoretical frameworks,
Hmm.
complex mathematical models. We're talking about simulations of the atmosphere and oceans. That's where the real power of modern climate science lies. It's become much more predictive in its approach, not just descriptive.
And here's where it gets really interesting. The emergence of this modern, more predictive climate science seems to be directly tied to the rise of something else: digital computing.
Absolutely.
Yeah.
Without those powerful computers, we wouldn't be able to handle the massive calculations needed to simulate something as complex as Earth's climate. Those early climate scientists, they were limited by what they could calculate by hand.
It's mind-blowing to think about the sheer number-crunching power needed to model the movements of heat and moisture in the atmosphere and oceans.
Those are the very things that shape our climates, right? Temperature, rainfall, all of that.
Yeah.
And those complex computer models, the ones that incorporate all these interacting processes, are really the heart and soul of modern climate research.
Hmm.
They've allowed us to get a much deeper understanding of how the climate system actually works.
Now, given all the attention on climate change these days, I think a lot of people might assume that climate science is solely focused on human-caused climate change, but your sources make it clear that this is a misconception, right?
You're absolutely right. While anthropogenic climate change, the changes caused by human activities, is a major focus of current research, climate science encompasses a much broader set of questions.
So it's about understanding the whole system, regardless of whether humans are involved or not.
Precisely. Scientists have always been interested in things like how the climate system behaves naturally, the long-term history of Earth's climate, what was the climate like millions of years ago, and all the natural factors that can cause climate to change, like volcanic eruptions, variations in solar radiation.
So it's not just about us and our impact, although that's clearly a huge part of the conversation now. It's about understanding the entire system, how all the pieces fit together.
And that leads us to a very fundamental question.
What exactly is climate? It seems like a simple term, but when you start digging into it, as your sources do, you realize it's more nuanced than you might think.
Right. Most people probably think of climate as just average weather over a long period of time.
Ah.
But your sources introduce this idea of the climate system, which includes all those interconnected components: the atmosphere, the oceans, ice, the land surface, and even all living things, what they call the biosphere.
It's amazing to think how interconnected everything is, and even human activity is part of that debate, right? Are we part of the climate system itself, or an external force acting upon it? It's almost a philosophical question about our place in the natural world.
It really is. And when you think about it like that, it kind of reframes how we approach climate science as a whole.
Then they dive into these different philosophical views on what defines a climate. There's the actualist view, which seems to focus on the actual conditions we observe.
Right, and that can be kind of narrow, like just looking at long-term weather statistics,
Hmm.
or much broader, considering the whole state and behavior of that entire interconnected climate system.
Then there are the model imminent views. These are a bit more abstract. Here, climate is defined in terms of a mathematical model. It's like an attractor of that model, a set of conditions the model tends to settle into over time, regardless of its starting point. It's kind of like imagine a pendulum swinging. No matter where you start it from, it will eventually settle into that regular back and forth motion. That regular motion is like an attractor.
And that's a really interesting concept because it brings in this idea of climate as a dynamic state that the system is drawn towards.
But as one of your sources, Smith, points out, there's a potential problem here. What a model does over an infinitely long period, in theory, might not actually reflect what happens in the real world, especially over timescales that are relevant to us humans. We don't have infinite time to wait and see how the climate evolves.
That's a really important point. We have to keep that in mind when we're using models to understand and predict climate change. And that's where Verndl's definition comes in, right?
Exactly. It's another model imminent definition, but it tries to be more grounded in reality. It defines climate as a distribution of climate variable values over a finite period, giving specific conditions. It's more practical, more tied to what we can actually observe and measure.
Right. It acknowledges that we can't just rely on these theoretical, infinitely long simulations. We need to be able to connect our models back to the real world.
And of course, how we define climate change then follows from how we define climate in the first place.
If you see climate as a model attractor, then climate change is a shift between those attractors caused by some external force. But if you define it by long-term weather statistics, then climate change is a systematic shift in those averages over time. And that shift could be caused by external factors, but also internal variability.
Internal variability.
Yeah, the climate system itself isn't static. It has its own natural fluctuations, cycles, and patterns that can cause changes even without any external influence, like those slow variations in ocean currents.
So even without any external forcing, the climate could still change due to its own internal dynamics. This whole idea of internal variability, which Katsov and Parker really dig into, it adds another layer of complexity, right?
Absolutely. It makes you realize that understanding and predicting climate change isn't just about figuring out the external forces. It's about understanding the internal dynamics of the system as well.
And it's fascinating that these fundamental conceptual questions, what do we even mean by climate and climate change, haven't really been thoroughly explored by philosophers yet.
There's a lot of fertile ground there for philosophical inquiry.
Absolutely. Okay, let's shift gears a bit and talk about the role of observation in climate science. We can't perform experiments on the entire planet, so how do we actually know anything about the climate system?
It really comes down to gathering as much data as possible from as many different sources as possible. And the variety of data that climate scientists rely on is truly impressive. You've got traditional weather stations on land, ships, and buoys in the oceans.
You mentioned airplanes and satellites too, right?
Yeah, they're collecting data from above.
Yeah.
And then you have all the paleoclimate data, which is information about past climates that we get from things like ice cores, tree rings, ocean sediments.
It's like putting together a giant puzzle, but the pieces are scattered across time and space.
And each piece comes with its own set of challenges, right? Gaps in the data, limitations of the instruments, questions about accuracy and consistency. And then there's the monumental task of piecing it all together into a coherent picture of how the climate has changed over time.
That's where all the hard work comes in, right? Quality control, data merging, transforming those raw measurements into usable data products. It's not as simple as just reading a thermometer.
No, it's a really intricate process. Let's take the example of those station-based data sets, the ones that record things like temperature, precipitation, pressure, and humidity at weather stations around the world. Some of those records go back well over a century, which is amazing.
But to get from those individual readings to a global temperature data set, there are several steps involved, right?
Yeah. First, you have to merge all those records from thousands of different stations, and then you have to check for errors, inconsistencies, make sure the data is as clean as possible.
And then there's homogenization, right?
That's a big one. It's about removing any jumps or trends in the data that aren't actually related to climate change. It could be due to changes in the instruments they used over time, or changes in the environment around the station, like a city growing up around it.
So there are a lot of potential biases and inaccuracies that you have to account for.
Exactly. And then finally, to create those global temperature data sets, you have to grid the data, which means assigning temperature values to areas of the globe where there aren't any stations.
I imagine there are different ways to do that gridding process, and different research groups might make different choices, right?
Absolutely. Which is why it's so significant that despite all those differences, all the major global temperature data sets show a remarkably consistent picture of warming, especially in the latter half of the 20th century. And the fact that an independent analysis by the Berkeley Earth Project confirmed those findings really adds to our confidence in the data.
So even with all those challenges and potential sources of error, we're still getting a pretty clear signal.
Right. Now, when you start looking beyond the surface up into the atmosphere and down into the oceans, things get even trickier. Getting those in situ observations, those direct measurements from those places, is much more challenging.
Especially historically, right?
Definitely. We have things like radiosondes, those instrument packages attached to weather balloons that go up into the atmosphere, and satellites in space, which are obviously really important.
But even those don't provide perfect global coverage. And the deep oceans, that's another challenge.
Yeah, the Argo float system, which gives us all this great data about temperature and salinity in the upper ocean, that's relatively new. Just a few decades ago, we had very little direct observational data from the deep ocean.
So how do you deal with those gaps in the data?
Well, they use statistical techniques to fill in some of the blanks, but one of the most powerful tools they use is called data assimilation.
Data assimilation. That sounds interesting.
It's actually pretty ingenious. They essentially blend our actual observations with forecasts from climate models.
So you're using the model to kind of fill in the gaps between the observations.
Exactly. The model provides a first guess, and then they use the observations to adjust that guess. It's the same technique they use for weather forecasting, but in climate science, they use it to create these long-term comprehensive data sets called reanalyses.
Reanalyses. So those are kind of like hybrid data sets, a mix of observations and model output.
Right. They're really valuable because they provide complete gridded data over long periods, both at the surface and in the atmosphere and oceans.
Mm.
But there's been some debate about whether we should consider them observations or not.
I can see how that would be a tricky question. They're not just raw measurements from the real world, but they're also not purely model output.
Right. It's a gray area, and Parker, in one of your sources, suggests that we should think of data assimilation itself as a kind of complex measurement process. It raises some interesting questions about how we define observation in science.
Definitely food for thought. Now let's go even further back in time to the world of paleoclimate. How do they reconstruct past climates when we didn't have any instruments back then?
They rely on proxy indicators, which are naturally occurring things that record information about past climate conditions,
Like what?
like ice cores, tree rings, those annual growth rings. They can tell you about temperature and rainfall in the past. And then there are things like fossilized shells of marine organisms that can tell you about ocean temperatures.
And sediments from the bottom of the ocean, they can tell you about all sorts of things, right?
Yeah, it's like digging up clues from the past using these natural archives. And Wilson and Boudinot, in another of your sources, make a good point. They argue that these proxy measurements aren't necessarily less direct than modern instrumental measurements. They just account for different causal factors in different ways.
So it's not just a simple hierarchy of direct versus indirect evidence, but a more nuanced understanding of how those different measurements relate to the climate variables we're interested in.
Precisely. But reconstructing past climates using these proxies definitely has its own unique challenges.
Like what?
Well, for one thing, many proxies are influenced by multiple factors at once. So you have to try to isolate the signal you're interested in. Like a tree ring might be affected by temperature, rainfall, soil quality, all at the same time.
And then there's the challenge of calibrating these proxy records, right? Matching them up with our relatively short instrumental records and assuming that those relationships have held constant over vast periods of time.
Yeah, that's a big assumption. And then you have the issue of spatial coverage. You might have a good proxy record from one location, but not from another. And the temporal resolution can vary too. Some proxies give you annual data, others only give you data every 100 years or even longer.
So it's a real detective story trying to piece together a coherent picture of past climates from all those fragmented clues. And it's remarkable how detailed those reconstructions can be given all those challenges.
They really are. And those reconstructions have been at the heart of some pretty heated debates, especially the ones that suggest that recent warming is unprecedented in the past few thousand years.
Yeah, those reconstructions have been a lightning rod for controversy.
But one of your sources, Vizère, suggests that our confidence in those conclusions often comes from what he calls variety of evidence reasoning. Basically, when multiple independent reconstructions, using different proxies and methods, all point to the same conclusion, it strengthens our belief that we're on the right track.
It's like having multiple witnesses to an event, right? Even if their accounts differ slightly in the details, if they all agree on the main points, it gives you more confidence that you're getting the story right.
Exactly. And another interesting point, this one from Watkins, is that the disunity we sometimes see in proxy data can actually be helpful. It forces us to really grapple with the uncertainties, to understand why those different proxies might be telling us slightly different stories.
That's a really thought-provoking idea. It's almost like embracing the messiness of the data can lead to a better understanding.
Exactly. Okay, so we've talked about how we observe the climate system,
Yeah.
both in the present and in the past. But to really understand how the climate works and to predict how it might change in the future, we rely heavily on another tool, climate models.
Right, those computer simulations we were talking about earlier.
Exactly. And it's important to remember that there isn't just one type of climate model. There's a whole hierarchy of models, from very simple conceptual models to those incredibly complex and detailed GCMs and ESMs.
The global climate models and Earth system models.
Right. And as you move up that hierarchy, the models get more complex, more detailed, and they require more computing power to run.
So at the simpler end, you have those energy balance models, the EBMs.
Yeah, they often focus on the overall balance of energy coming into and going out of the Earth system. Some of them are even zero-dimensional, treating the whole planet as a single point.
So very simplified, but still useful for understanding some basic principles.
Right. Then you have the Earth system models of intermediate complexity, the EX. They include more of the key components like the atmosphere, oceans, land, and ice, but they still use simplified representations of some of the processes. They're good for simulating long-term climate changes over thousands or even hundreds of thousands of years.
And then you have the big guns, the GCMs and ESMs. These are the ones that simulate the three-dimensional motions of the atmosphere and oceans, and they try to account for all those interactions between the different components.
Right. And they've evolved from those numerical weather prediction models that we use for forecasting the weather.
So they're based on the same fundamental physics, but they're designed for longer-term simulations.
Exactly. And the key thing to understand about those models is that they divide the Earth into a three-dimensional grid of cells, and then they use numerical methods to solve the equations of fluid motion at each grid point.
And as computing power has increased, they've been able to make those grids finer and finer, right?
Exactly, which means they can capture more detail. But even with today's supercomputers, many important processes still happen at scales that are too small for the models to resolve directly.
Like clouds, right?
Yeah, clouds are a big one. And that's where parameterization comes in.
Parameterization, you mentioned that before. It's about representing those small-scale processes in a way that the model can handle, right?
Right, it's a real challenge. It often involves a mix of theory and empirical relationships derived from observations. And it's an area where machine learning is starting to play a bigger role.
So you're using AI to try to improve the representation of those small-scale processes,
Exactly. And then there's the whole issue of model tuning or calibration.
which is basically tweaking the model parameters to improve its performance, right?
Yeah, making sure the model's output matches up with what we've observed in the real world. And that can be a pretty subjective process. Even though they're using more automated methods now, there are still choices involved in what data to use, what aspects of the model to prioritize, and how to define a good fit.
So even with these really sophisticated models, there's still a human element involved, right? Human judgment and decision making.
Absolutely. And that's where the philosophical questions come in, because those decisions can be influenced by things like values, societal priorities, even political considerations.
So the models aren't purely objective representations of the climate system. They're shaped by human choices and perspectives.
Right. And Winsberg and others have written about this. They argue that we need to be aware of those potential influences and how they might shape our understanding of the climate system.
That's really interesting. Okay, so we've talked about how these models are constructed. What do scientists actually do with them once they're up and running? What are the main uses?
Well, one important use is to characterize aspects of the climate system that we can't observe directly,
Like what?
like internal variability, for example. We can run model simulations to understand those natural fluctuations in the climate system, even without any external forcing.
So it's like using the model to see what the climate would do on its own without any human influence.
Right. And they also use models to estimate key parameters, like the equilibrium climate sensitivity, which is a measure of how much the global temperature would rise in response to a doubling of CO2.
And models are also crucial for explaining and understanding how the climate system works, right? It's not just about simulating what might happen, it's about understanding why it happens.
Absolutely. Parker has argued that models can act as surrogates for observations in some cases, allowing us to test hypotheses and explore different mechanisms. And Held has emphasized the importance of having a hierarchy of models, from simple to complex, to help us understand why the climate system behaves the way it does.
So it's like having a toolbox of different models, each suited for a different purpose.
And of course, a major use of models is to make predictions about the future climate.
That's what everyone wants to know, right? What's the climate going to be like in 50 years, in 100 years?
And the models are the best tools we have for that. Now, we can't predict the exact weather conditions on a specific day far in the future. That's just not possible. But we can use models to project longer-term trends, like average temperatures and rainfall patterns over decades or even centuries.
And those projections depend on what emission scenario we choose, right? What we do as a society to reduce greenhouse gas emissions will have a big impact on what the future climate looks like.
Absolutely. And it's not just about future emissions. It's also about how the climate system will respond to the changes that are already locked in. And that's where understanding past climates and those paleoclimate analogs you mentioned earlier can be really helpful. They give us a glimpse into how the Earth system has responded to large-scale changes in the past.
So past climates can help us understand potential future climates.
Right. Now, there's an ongoing debate about the best approaches for future model development. Some researchers argue that we need to push towards even finer resolution down to the kilometer scale so that we can explicitly simulate more processes directly without having to rely so much on parameterization.
So more detail, less approximation.
Exactly. But that requires a huge amount of computing power. Others argue for a more moderate approach, focusing on intermediate resolutions and leveraging the power of AI and machine learning to improve those parameterizations and gain efficiency.
So it's a trade-off between resolution and efficiency.
Right. And Baldister Packety and others have called for a more pluralistic approach, basically saying we need a diversity of models, each suited for different research questions, and we need to support all those approaches.
It makes sense. There's no one-size-fits-all solution. So given all these different models, how do we know which ones to trust? How do we evaluate their performance?
Model evaluation is a crucial part of climate science. Individual components of a model are tested in isolation, and then the fully coupled models are evaluated as a whole. And a big part of that happens through international collaborations like the CMIPs, the Coordinated Model Intercomparison Project.
CMIPs. What are those?
Basically, climate modeling centers around the world run a standardized set of simulations and then compare their results with each other and with observations. It's a way to see how well the models are able to reproduce the observed climate.
So it's like a benchmarking exercise. You're comparing apples to apples.
Exactly. And those comparisons are crucial for building confidence in the models, for seeing whether they're adequate for certain purposes. Like the IPCC, for example, has used those model data comparisons to support their conclusion that human emissions are the main driver of recent warming.
But drawing conclusions from those model data comparisons isn't always straightforward, right?
No, it's not. Parker and other philosophers of science have pointed out several complications. For one thing, the observations themselves have uncertainties. And the initial conditions you use to start a model simulation can never perfectly match the real world.
Because the climate system is chaotic, right?
Exactly. And then there's the issue of tuning. If you've already adjusted the model parameters to improve its fit with past observations, can you really use those same observations as independent evidence of the model's skill?
It's like using the answers to a practice test to study for the real exam.
Exactly. Frisch has argued that we should focus on moderate predictivism, which means seeing if the model can accurately predict things that weren't used in its tuning.
So can it make successful predictions about new data?
Right. And many argue that we should go beyond just looking at model data fit when we evaluate models. We should look at things like whether the model's processes are physically plausible, whether its results are robust to different assumptions, whether it can reproduce key features of the climate system.
So it's not just about matching the numbers, it's about understanding why the model is getting those numbers.
Exactly. And that leads to the question of model improvement. How do we make these models better?
That's a big challenge, right?
It is. Some researchers have argued that the complexity of these models, the way that different components are all interconnected, and the use of certain kludges or fixes that aren't always physically justified can make it really hard to pinpoint the sources of errors and systematically improve the models.
So it's not always clear how to fix what's broken.
Right. But others have pointed to examples where scientists have been able to successfully diagnose and address model errors, suggesting that it's not impossible. It just requires a really deep understanding of how the models work.
So there's reason for both optimism and caution.
Exactly. Okay, we've covered a lot of ground here. We've talked about how we observe the climate, how we model it, how we evaluate those models.
Now let's get to the heart of the matter. What does all this tell us about the human impact on the climate system?
Well, the idea that human activities, particularly burning fossil fuels and emitting CO2, could change the climate, that idea goes back over a century to a scientist named Svante Arrhenius.
Wow, that's a long time ago.
It is. And by the mid-20th century, scientists were starting to raise real concerns about rising CO2 levels. And that led to the formation of the IPCC, the Intergovernmental Panel on Climate Change, in the late 1980s.
The IPCC, they're the ones who provide those big assessment reports on climate science, right?
Yeah, they synthesize all the latest research and provide a comprehensive overview of the state of the science.
And they've played a key role in establishing the evidence for both the detection and the attribution of climate change.
Exactly. Detection is about showing that a statistically significant change has occurred, a change that can't be explained by natural variability alone. And the IPCC's confidence in that detection has grown stronger with each report.
And then attribution takes it a step further, trying to identify the causes of that change.
Right. And that involves using both our physical understanding of the climate system and those quantitative studies that compare observed patterns with model simulations.
So you're seeing if the observed changes match what the models predict would happen if humans were influencing the climate.
Exactly. And those fingerprint studies, as they're called, are a key part of attribution. And the IPCC's confidence in attribution has also grown significantly. They now say it's extremely likely that human emissions are the main driver of the warming we've seen since the mid-20th century.
And that leads to the idea of a scientific consensus on climate change.
Right. While focusing solely on the percentage of scientists who agree can be a bit simplistic, the overwhelming level of agreement among climate experts is a clear indicator of the strength of the evidence.
And Ores has written extensively about this consensus. She points to the successful predictions of climate models, the resilience of the findings to attempts at falsification, the consilience of evidence from multiple lines of research. All of that supports the idea that we're seeing a real human impact on the climate.
And Lloyd has emphasized the importance of robustness, the fact that those conclusions hold up across a range of different models and assumptions.
But it's also important to acknowledge that there have been dissenting voices, right? Scientists who have raised alternative perspectives.
Absolutely. Katsa, for example, has argued that the attribution of warming to human activities hasn't been subjected to sufficiently rigorous testing, particularly when it comes to the uncertainties associated with natural variability.
So he's saying we need to be more critical of the evidence, that we shouldn't just accept the consensus view uncritically.
Right. But de Thier has countered that argument, suggesting that the estimates of human influence are actually relatively insensitive to those uncertainties in natural variability.
So it's an ongoing debate, and it's important to consider all sides of the argument.
Absolutely. Now, another area of active research is probabilistic event attribution, which is about understanding the role of human influence on specific extreme weather events, like heat waves and floods.
So it's about trying to say whether climate change made a particular event more likely or more severe.
Exactly. But it's a tricky area. There's still a lot of debate about the methods and how to interpret the results. Some argue that we might be overestimating the human influence, others that we might be underestimating it.
So it's an area where more research is needed.
Definitely. Okay, now let's talk about future projections. We rely on climate models to tell us what the climate might be like in the future, and those projections are often presented as ensembles, meaning we run the models multiple times with different assumptions.
And there are different ways to interpret those ensembles, right?
Yeah, there's the probabilistic interpretation, which focuses on assigning probabilities to different outcomes, and then there's the possibilistic interpretation, which is more about exploring the range of possible futures without assigning specific probabilities.
And there's also the hawk moth effect to consider, right?
Yeah, that's the idea that small errors or uncertainties in the models could lead to overly precise probability forecasts. Basically, the model might be giving you a very specific answer, but that answer might be based on shaky ground.
So we have to be careful about overinterpreting those probabilistic projections.
Exactly. And the IPCC, in their reports, often uses what they call imprecise probabilities, acknowledging the inherent uncertainties.
So instead of saying there's a 60% chance of this happening, they might say there's a 50 to 70% chance.
Right, they're trying to be more transparent about the level of uncertainty. And there's also been a shift away from treating all models equally, what they call model democracy.
So not all models are created equal.
Right. They're starting to weight models differently based on how well they perform against observations and other criteria.
Right.
But figuring out the best way to do that weighting is still an ongoing challenge.
It sounds like there's a lot of subjectivity involved there.
There is. And then there's the philosophical question of model agreement. Does agreement between different models strengthen our confidence in their projections?
You would think so, right? If multiple independent models are telling us the same thing, it seems like that would give us more confidence.
It seems intuitive, but Parker and others have raised some important cautions about that. They argue that we need to be careful about simply assuming that agreement equals reliability.
So just because the models agree doesn't necessarily mean they're right.
Exactly. It's more complicated than that. Winsberg has proposed the idea of robustness analysis, which is a way to systematically explore the sensitivity of model results to different assumptions.
So seeing how much the results change when you tweak the model in different ways.
Right. And that can help us to understand which aspects of the projections are more robust, more likely to be accurate.
It's all about understanding the limitations of the models and interpreting the results cautiously.
Absolutely. And for practical applications like planning for local impacts, we often need to downscale those global model projections to finer scales.
So taking those big picture projections and making them more relevant to specific regions or cities.
Right. And that introduces another layer of uncertainty because those downscaling methods have their own limitations.
It seems like uncertainty is a recurring theme in climate science.
It is. And we're also seeing an increasing use of storyline approaches and tales of future weather, which are more narrative and accessible ways to communicate potential climate futures.
So instead of just showing graphs and numbers, you're trying to tell stories about what the future might be like.
Exactly. It's a way to make those projections more relatable and understandable for people.
Now, we can't talk about climate science without acknowledging the controversies that have surrounded the field.
Right. There have.